So, do you remember on your test? So why aren't you moving through the floor right now? You're being pushed down. And what's the name of that force? Yes. So it has a normal force that is perpendicular to the slope. So we have a normal force. Let's make this 45. I'm trying to figure out the best way of drawing this so that it looks nice. So we have a downward force. This would be the weight. And we have a normal force that would be 90 degrees off. So we have two forces being applied to this box. We need to get the net force. So we're going to have vertical forces. Let's do horizontal first. So horizontal. So this force right here, this upward force, has a horizontal component and a vertical component. And we can move this side of it to be right here so that they connect up. But it has a vertical and a horizontal. So we can take this and do a horizontal and a vertical. So the horizontal force so if we take, we need to figure out what this angle is. So what would this angle be right here? No. So let's imagine this continue down right here. This is 90 degrees. This is theta. That's 90 degrees. This angle right here would be 90 minus theta. Right? So let me again. I'm trying to illustrate this. So suppose we have a force right here at some angle. So this would be theta. So this is 90. The sum of the angles of a triangle is 180. So this is 90. That's theta. This angle right here has to be 90 minus theta. And so if we draw a vertical arrow right here and a horizontal, we can look at this force. This was theta minus 90. This would be 90. So that means this angle right here is theta. So that means that if we draw this force right here, this angle right here is going to be theta. You could also use the fact that this is 90 minus theta, but I don't like plugging in 90 into the signs. So the opposite of this angle is sine. So the horizontal force, so it would be this normal force times sine of theta. And looking at the vertical, force, well, we have your weight. is pointing down. Well, I'll just. So we have our weight. So force times weight. And we also have, it would be the cosine of this, your normal force times cosine of theta. So these are our two vertical forces. Let's see. What's the trick here? Oh, yeah. So, remember Newton's third law. For every action, there's an equal and opposite reaction. So that means that these two forces have to be equal. Equal. I'm trying to think of the best way of explaining this. I'm going about it the wrong way. I wanted to solve it this way before I showed the slightly easier version of it, but so this isn't working out. Having a brain fart. Alright, I'll just go ahead and present the better way of analyzing it. So we've been doing up and down and left and right. Your axis can be in any direction. Or let me make this. I've been doing it. So again, we have a downward force. And we have a normal force. So this is the normal, this is the weight. I tried solving it by setting my axis like this. So I have a vertical axis and I have a horizontal axis. I was getting stuck on solving it that way. It's kind of difficult to solve. But wouldn't it be so much easier if I just rotate this so that this is on a flat surface? So let's do that. Instead of drawing my vertical axis like this, I'm going to draw my vertical axis to be like that. And then I'm going to draw my horizontal axis to be like this. So this is my new vertical, and this is my new horizontal. So if I zoom in, I'm going to draw my new axis. And then I'm going to draw a color. So this is my axis. So this is my vertical axis, my y-axis, and then I'm going to put my x-axis to be like this. So this is going to be my horizontal axis, or my x-axis. And again, I could really think of this box as being a single point. I'm going to put that single point right here. I have a downward force. This would be the weight. And then I have a normal force right here. By rotating the axis, I made this problem a whole lot simpler, right? Is it moving in the vertical direction, the new vertical? Is it? So it's going into the slope? It's moving down here? So again, I'm rotating it. So imagine, oh, let me draw like that. Imagine now it is moving in this direction, right? It is not moving into the surface, and it's not floating off the surface, right? So it's moving down here. So in our old system, where we had the vertical like this and the horizontal like this, yes, it's moving in this direction. But when I rotate this, it is moving in this direction, right? It is just moving to the right in the horizontal direction. So by rotating my axis, I see that the vertical, let me put it in quotation, the vertical velocity is 0. My new vertical velocity is 0. It is just moving down the slope. So last time, or my attempt at least, my attempt was to take this normal force and map it so that it goes vertical with gravity. What I'm going to do instead is take the weight and map it to my new axis. So again, this is an angle of theta. This would also be theta. And what I'm going to do, again, if I rotate it, we see that, again, green is my new axis. This is going to have a right component and a down component. Or drawing it equivalently, it's going to have a down component and a right component right here. So FW can be broken down into a horizontal component and a vertical component. The horizontal component, again, the horizontal, is going to be opposite of theta. So that would be FW times sine of theta. And the vertical component is going to be FW times cosine of theta. And Fw was just m times the acceleration of gravity g. So, in other words, that's m times g times sine of theta. And this will be m. I'm going to let g be positive. I'm going to let g be positive 9.8 meters per second squared. So that my vertical arrow right here is negative. So I plug in a negative right here, mg cosine of theta. And then this would be positive. And my normal force, again, my normal force was pointing upward toward the box, right? So my normal force is only in the new vertical. So it's 0 newtons here, and for the vertical, it would just be Fn. It's all vertical. And what we can see here is that it is not moving in the vertical direction. There is no force in the two force, because there's not accelerating into the slope, into the incline. This is called an incline plane. Because it's not going into the inside of the plane, it's only sliding down it. I know that in the vertical direction, that the sum of vertical forces has to equal 0. So that means these two must be equal. Fn has to equal negative mg cosine of theta. Or I should say m plus has to equal 0. So that means Fn has to equal m times g times cosine of theta. Moving this to the other side. And that means my only force going down the slope has to be these two added together. So my force down this slope, so the net force I could say this. So the force in the y direction has to be 0. And the force in the x direction has to be the sum of these, so mg sine of theta. So this is the force in the new horizontal. We can solve for acceleration. So remember that force is ma. To solve for acceleration, we divide both sides by mass. So force divided by mass is equal to acceleration. So we can get the acceleration in the horizontal direction would just be g times sine of theta, right? So that means, going back up here, the acceleration down the slope is g times sine of theta. Let me re-explain everything. I feel like I did a terrible job. So, We have a box on an inclined plane that is moving down the slope. The inclined plane is at some theta angle. This box has a mass m. So it's moving down the slope. What we want to do is rotate the axis so that the horizontal axis is parallel to the slope, and the vertical axis is perpendicular. Because the box is sliding down the slope, only the new horizontal axis will have an acceleration. So I'm going to rotate this axis so that I'll even do it at the midpoint of the box. So this will be our new y, this will be our new x. We see at this point there is a downward force. This would be m times g. And we see that there is going to be a upward force, which would be the normal force. Since the box isn't moving in the new vertical direction, we only have to look at the new horizontal. So this image can be broken up. So we're going to have this mg is going to be mg sine of theta, and a downward force here, which would be mg cosine of theta, and then we have the normal force. I'll draw it up here. This was the normal force. And to illustrate how I chose sine instead of cosine, if we were to zoom in on this, so we have a triangle here that's theta. We have our y. we have mg so this was our x. So again, we can draw a right angle here. So this would be a downward. I'll draw it red. So this would be our downward, and this would be our vertical, our horizontal. I mean, this will be our vertical. So this angle right here is theta, and we can break this one vector into components. We can break it into a down component, and we can break it into a right component. This right component will be on the horizontal axis right here. So opposite. Do you see why I'm drawing it right here and here? It's just mirror images, so you can draw it so where these angles connect up like this, from the tail, head, to tail, to head. It's also stuck on this line right here. But opposite, so in this direction, opposite is sine. So it would be mg sine of theta. And adjacent to it is mg cosine of theta. So from this image, we see that Fn plus, so this is pointing downwards, so I'd use a negative, mg cosine of theta is equal to 0. And this is the vertical. And in the horizontal, so the sum of y's equals 0. And in the horizontal, we only have one force, or f of x is equal to mg sine of theta. We can get acceleration in the x, so fx is going to be equal to some mass times the acceleration in x. We can just divide fx, so fx divided by mass is ax, so we can divide both sides by mass. And fx over m is just acceleration. So the acceleration in our new horizontal is going to be g times sine theta. And then we can use standard kinematics to solve this. We have the acceleration is going down the slope. So that means that delta x is equal to initial velocity times t plus 1/2 times ax times t squared. We don't know time, so maybe not. That's not the best one to use. We do know delta. Let's try to eliminate time. Which one does it use time? That would be this one. Vf squared is equal to vi squared plus 2 times the acceleration times delta x. So however long this path is, we can figure out the final velocity. The final velocity is just the square root of the initial velocity squared plus 2ax delta x. So let's get a particular problem. So let's make this 4 meters tall. Oh no, let's make this 3 meters tall and this 4 meters. Let's say that the box has a mass of 5 kilograms and an initial speed of 0 meters per second. How fast will it be moving at the bottom? So how fast will it be moving right here? Technically, it would be, since it's moving from here, technically it would be more like this. Right when that left corner is right here. But, let's see. So, we're going to change our axis. We need to figure out what this angle is. And we also need, so we need to change our axis. We need to redraw this. So that's horizontal instead. So we basically have a box, 5 kilograms, that's moving to the right. Gravity is pointing downward. So gravity is going to give it a mass of mg. It has a normal force on it. So to figure out this component here, we need to figure out this angle. So this angle right here is going to be the inverse tangent. So theta is the inverse tangent of opposite over adjacent. This distance right here, I'm going to call my delta x. My delta x is going to be the square root of 3 squared plus 4 squared, which is equal to 5 meters. It's a famous 3, 4, 5 triangle. So delta x is equal to 5 meters. My acceleration, because this is we can continue this down, this angle right here, so if I were to draw this like this triangle right here, these are two similar triangles. This angle right here is theta, right? No, it's not. I wouldn't draw this line right here. I would need to do a vertical line like this. I would draw this line right here up. So this angle right here is going to be theta. So opposite of this angle is sine. So my AX is going to be mg times sine theta, where g I'm letting just be positive. The reason why I'm letting g be positive is because I'm drawing arrows at the same time. The arrows indicate the direction, and so I want to use positive values everywhere in, and let the arrows represent whether or not it's negative or positive. So then we can solve this. Final velocity squared equal initial velocity squared plus 2 times ax delta x. So our final velocity equal the square root of vi squared plus 2ax delta x. Our initial velocity is 0. So that's 2 times ax delta x, which equals square root of 2 times mg times sine of theta delta x. Sine of theta was the inverse tangent of 3/4. I'll go ahead and plug values in. Square root of 2, our mass is 5 kilograms. Probably shouldn't use the answer. G was 9.8. 10 times sine of tangent. And delta x was 5. So plugging that all into the calculator. You'll also notice I didn't solve for theta. We should already know that it's, if you remember, it would be 36.86 989. So theta was 36.86989765 degrees. But doing this, we get 17.14648 meters per second. Later on in the year, we will revisit this problem, and we will see that there is a super easy way of solving this, where all this mathematics just disappears. But does this make sense? Did you understand why I did sine and how I got this angle and drew this? That's the most difficult part, is the geometry. Doing the geometry and figuring out where your theta is. Because, for example, if I did this instead, if I told you this angle, then this would be mg cosine of theta. And if I did this angle here, then it's mg sine of theta. You just have to realize when you switch angles, you have to keep making right triangles and figure out where theta keeps. You could have also, by the way, in case you didn't know this, cosine of 90 minus theta is sine of theta. And sine of 90 minus theta is cosine of theta. I think there could be a negative in there somewhere. Let me see. Cosine. Yeah. Sine is equal to cosine 90 minus theta, and cosine is equal to sine 90 minus theta. Just some trigonometry stuff. But generally, you don't want to do this. One of the main reasons you don't want to do this is in real science, we don't use degrees. We use radians. So we would do cosine of pi over 2 minus theta, and the sine of pi over 2 minus theta is equal to cosine of theta and sine. So you have to make sure you know what your theta is in, if it's in degrees or radians. But if you can write your answer so it doesn't matter, if you can eliminate trying to use 90 or pi over 2, that's the best thing to do. And in most sciences, we do use radians. Do you know why? You know what radian is? So if we have a circle, if we had a circle where the radius is 1, and if we drew this, so it's a unit circle, so the radius is always 1. If we draw this angle so that this distance right here, the length of this arc, is equal to this angle, we call that a radian. So the distance right here is, so for example, 90 degrees is this. So if this was pi over 2 angle, 90 degrees, so pi over 2 radians, the distance right here on a unit circle is equal to pi over 2. So we get that the arc length is equal to r times theta, where theta is in radians. That's the reason why is we can directly use theta as a real number instead of angle.